Everyone hear me? Am I coming through okay? Can people see me? And can I move this? Okay, brilliant.
Yes, we can.
Okay, so my name is, okay, my name is Jessica Barnes. I'm a second year PhD student here at the Open University. And today I'm going to be talking to you about the water content and hydrogen isotopic composition of the lunar magma ocean.
Just use the arrow buttons at the bottom there and they'll snap right to the next slide.
Oh, yes, brilliant. Cool. Thanks. Okay, so we've heard a lot over the last couple of days at the conference that the legacy of the Apollo era was that of an anhydrous moon. And we also have heard that since the 1990s and early 2000s, several orbiting spacecraft have detected variable but significant quantities of hydrogen, hydroxyl, and water ice all over the lunar surface. And this really prompted a reanalysis of the lunar Apollo sample collection, starting off with work by Alberto Sal and his group in 2008. And a lot of this work has focused on the products of lunar basaltic volcanism, particularly volcanic glasses, melt inclusions, and apatite in the rock samples. And it's been shown that these contain variable proportions of volatile elements, particularly fluorine, chlorine, and hydroxyl OH, with up to 2,000 parts per million hydroxyl in apatite from Mare basalt. So far, the lunar interior is calculated to contain up to 400 parts per million water, like we just heard from Lindy's talk. An interesting feature of apatite is that we can measure apatite and glass beads, is that we can work out and measure the isotopic composition of the hydroxyl. And this signature can allow us to put a source region, fingerprint a source region for that water. Okay, so now focusing in on apatite. So first of all, I want to say that apatite is an important mineral. It's the most commonly occurring hydrous mineral in lunar rock samples. And on the left-hand graph, we've got delta D SMO, where SMO is standard mean ocean water, and that's delta D in per mil, versus the hydroxyl content in parts per million on the x-axis. And what you'll notice, this is all data from the literature, so conference proceedings and publications. You can see that there's a very wide spread in OH content for the Mare basalt samples, and also they're quite heterogeneous in their delta D signatures. If you look at what's been published for the crust samples in comparison, they're quite restricted in terms of their OH. They're relatively drier. But they do show a spread in delta D. Now, if we take that apatite data for delta D signatures and we compare it to other objects in our solar system, we can see that the delta D signature, in the right-hand graph in pink, we can see that those apatite data are quite comparable to what you see for carbonaceous chondrites and also some analyses of samples from Mars. So moving on, what am I actually working on? So, as I mentioned, apatite is an important mineral. It's commonly occurring in lots of different rock samples. And I'm interested in looking at the hydrogen isotopic composition and water content of, people hear me? Yes. Of water content in apatite grains from highland samples. So the samples we've been working on to start with are troctolite 76535. It's approximately 4.3 billion years old, and it's relatively unshocked. We've also looked at norite 78235, which is a bit older, 4.44 billion years old, and this sample is shocked. Now, both of these samples are part of the magnesium suite, and if we go back to our models of lunar magma ocean formation, the magnesium suite, in general consensus, likely formed after the overturn event and formed from magnesium-rich melts, which possibly rose diperically through the lunar interior. Once they reached the lunar crust, likely assimilated variable amounts of aircrete, and then were intruded into the lunar crust where they formed plutons. So these rocks of the magnesium suite can really help us to understand the water content of the products of lunar magma ocean crystallization. So how do we analyze our samples? We use Apollo rock thin sections, and we use secondary electron microscopy to map our samples using X-rays. And where we see enrichments in calcium and phosphorus, that indicates the presence of a phosphate. And we can use energy dispersive spectroscopy to actually identify apatite. Once we know where apatite is within a sample, we can then move on to secondary ion mass spectrometry. And we have here at the Open University a Kamika NanoSims 50L, which we use for these analyses. Typically, we use a primary cesium-positive probe of around 440 picoamp, and we raster an area approximately, depending on the sample, 10 by 10 microns in area. And we collect the secondary negative ions, which are given off for hydrogen, deuterium, 18 oxygen, and 13 carbon. By looking at the deuterium to hydrogen ratio, we can get an idea of the delta D signature, and then this is what we use to characterize or to give a source region for that water. So this is a similar plot to what I showed a bit earlier, and here we have the troctolite data in red and the norite data in blue. And the first thing you'll notice is that the troctolite sample is very depleted in terms of OH. It's very dry, typically less than 60 parts per million hydroxyl, and it shows a wide spread of delta D. In stark contrast, the norite has is quite homogeneous in terms of delta D, yet shows a spread in OH content. And this is likely due to fractional crystallization. So let's compare this now to what we have seen earlier from the literature. So these are the fields again for Mare basalts and cross samples. And one of the troctolite points is very comparable to work presented at this year's LPSC by Katie Robinson. The others are quite elevated compared to most Apollo sample apatite compositions. But that's probably due to a counting statistic inherent to the analyses. So we can probably discount those three elevated troctolite data points. But the troctolite, the one that's at 700 per mil, is well within the range of other cross samples. However, what's particularly important about this data is that the norite falls outside the realm of Mare basalts and also cross samples. So it seems to be a bit of a unique sample. If we compare this to what we know about, what we understand about source regions, around 100 per mil is the delta D signature for carbonaceous CI type chondrites. And the terrestrial range, something's going on here. The terrestrial range is in the grey box. So what we can see is that most Apollo samples are well above the terrestrial range. However, the norite data we're presenting here is actually within the terrestrial range and quite comparable to what we know about values estimated for bulk Earth, around -47 per mil. So I mentioned earlier that we can use the water contents or hydroxyl contents that we measure in samples, whether it's glasses, melt inclusion, or apatite, to model what we know, to model the water content of the lunar interior. However, excuse me. However, we can't really use the troctolite sample for this modeling because it's likely been altered by a post-crystallization metasomatic event, probably by a chlorine-rich melt. And thus, we think its halogen content, the halogen content of the apatites have likely been disturbed. So we'll just concentrate on using the norite data when we go in to do the modeling in the next step. So what we wanted to do was estimate the water content of the noritic melt at the time apatite crystallized, roughly between 95 and 99% crystallization of the magma. And to do this, we used a apatite hydroxyl partition coefficient of about 0.3. Then we subtracted or took away the effects of crystallizing nominally anhydrous minerals. And we obtained a value of around 300 ppm water for the norite parental melt. Now, I mentioned earlier that the norite is probably, according to popular hypothesis for the formation of the magnesium sweep, it's probably a product of magnesium-rich melts from the lunar magma ocean, which rose up through the lunar mantle and likely assimilated aircrete material. Now, if we use this and then what we understand about the evolution of the lunar magma ocean and what we know about incompatible elements, we can assume that the magnesium-rich melts would have been characterized by relatively low water content and the aircrete to be much richer in terms of water content. such that possibly what we're measuring in this norite mostly comes from the earthcrete material this melt assimilated. And this is in quite good agreement with what was published earlier this year by Hui et al., who shows that earthcrete may contain up to 1.4 weight% water.
We've got 80 seconds left.
80 minutes. So what have we learned? So the parental magma for the norite was relatively wet, and it potentially records the delta D signature of the lunar magma ocean, because this sample hasn't really undergone any degassing. In contrast, modelling of the younger Mare basalts shows that their source regions in the lunar mantle was relatively wetter, and those samples are characterized by delta D signatures quite similar to carbonaceous chondrites once you take out the effects of degassing. And this may suggest that we've seen a late addition of volatiles into the lunar mantle. So moving on to conclusions, we now know that the lunar interior is relatively wet, and we think that the similarity in hydrogen isotopic composition of the lunar norite, which has likely not seen very much degassing, and the bulk Earth, actually argues that volatiles in the primordial LMO were inherited from the proto-Earth, which is work that was presented, I think, a couple of weeks ago by Alberto Sal and his group. And this is in good agreement with the hypotheses that suggest that the moon actually accreted largely from proto-Earth material, and it also suggests that volatiles may persist the moon-forming event. Thank you.
Jessica, we've got some questions. Let's see, Alberto had a question. What is the effect of metamorphism and solar wind implantation on the apatites from norite?
Sorry, what was that question? The metamorphism and
Solar wind implantation.
I think it's quite difficult to assess the effects. And of solar wind, I don't think there is any effect, because we've looked at samples of different CRE ages, and there doesn't seem to be any implication that we're analysing any solar wind. And on that strain, we don't think we're analysing any terrestrial contamination either. We can move away from that using the SIMS.
There's also a question from Rishitosh. You basically measure OH. How do you convert your measurements for measurements of H2O?
Okay. So OH to H2O, what we do is is someone shouting at me? No? No? Thought I heard mine. To convert from OH to H2O, we basically divide, I think what we do, we divide analyze our value by 9 to get H2O, and then if you've got H2O, times it by 17 to get OH. So it's basically twice as much hydroxyl for water. I hope that was, sorry, I was a bit convoluted in the way I said that.
I'd also like to know if there is any cosmogenic contribution to the crust sample.
No, I don't think so. As I said, we've looked at samples of different cosmic ray exposure ages, and there doesn't seem to be any trend with delta D or OH for varying for samples with different CRE ages. Excuse me.
Okay, I think we got all the questions, so I think we are ready to move on. Thank you very much.